computer. All right. Zero product property, extremely valuable property. If two things are multiplying together, and I'm going to actually show you the answers so that otherwise I'm going to use different variables, letters. I'll give you a second to print. Okay, I'll try and go slow. I'm going to go over to the answer document so that otherwise I might accidentally use different letters than what are here. So the point of the zero product property is however many numbers you have multiplying. And I'll repeat myself, Alec, when you get back from printing, because this is that important. If any bunch of numbers multiply together and you get an answer of 0, that equation is true if any one of the numbers that are being multiplied is equal to 0. And I don't know if you're back with printing yet. I know I've got to be careful with time. So you're going to be using the zero product property to solve polynomial equations. I'm going to leave this up for a little bit and talk about it a couple of times. So you're going to have polynomial, when you were factoring, those were expressions. They didn't have an equal sign. The problems in today's homework are going to be polynomials with equal signs. And the very first thing you have to do is get one of the sides equal to 0 through addition and subtraction. Then, once you get one side equal to 0, you're going to factor the polynomial, unless sometimes you'll be given an equation that's already nicely factored for you. You'll appreciate those when they show up, but they're not tonight. So you are going to factor your polynomial just like we were going over. Then once you're factored, take each individual factor, set it equal to 0, solve each one of those equations, and all of those solutions are solutions to the polynomial equation. So is everyone ready for me to scroll, or do you need me to wait here? Okay, I'm going to wait. And how about I just say it again? So you just hear it again. The zero product property is the key to this working. If we didn't have the zero product property, actually, I'm about ready to. If we didn't have the zero product property, we'd be okay because our technology will solve it for us anyway. Yeah, ha ha ha. So I realize as technology comes in, there's a lot of math that it will do for us. These are important properties of a language that science uses. And I don't know how things are going to change in the future as technology becomes, as it has become so prevalent. I'm sure things will change. But for now, I need to make sure that you know the language that's expected for you to know as you go into your science courses so that your science teacher does not have to teach this to you. Zero product property. Make one side 0 before you do anything. Are you ready to see an example? Okay. Tell me in chat if you need me to go back. Oops, those are the answers. I want to start with non-answers, the questions. That's right. I was kind. I did start you off with some lovely factored problems. So to point out to you, okay, Actually, it is posted on Google Classroom with the classwork if you need to write it out later. Right now, I've got to keep moving or I'm going to run out of time in class, and none of you are going to stay after class. So, well, I can't say none of you, but people don't want to stay after class usually at the end of the day. Okay, equals 0. That is very important. You have a polynomial that is already in factored form. So we're going to focus on first the steps to take once it's factored. And that is, notice your 3 factors, set each one equal to 0. X equals 0 is already telling me an answer. I need to add 3 to both sides here, and I have my next solution. And then I'm going to first subtract 5, and then divide by 2. And I have 3 answers. And I'm assuming you realize that negative 5 halves is negative 2.5. You can write it either way. I don't care which way you write it. So we are getting 3 solutions to this equation. And when you have just the quadratics, you would only get 2 solutions. Do you remember that? When you had quadratic equations and you were solving and you'd get 2 solutions usually? Well, now it's however many linear factors we have determines up to how many solutions we might have. Now, number 2, it's already set equal to 0. So I am going to look at all of my factors. I have number 3, I have x plus 4, and I have x minus 1 quantity squared. So maybe some of you see that I don't need to write what I'm about to write, but I'm just going to throw it out there. I need to set everything that is a factor equal to 0 and see what I get. So I've got 3 equals 0, x plus 4 equals 0, and parentheses x minus 1 squared equals 0. Now, what value of x will allow 3 to equal 0? None. Now, when you see just a constant multiplying in front, as opposed to, I want to emphasize over here, you had an x. And when I wrote x equal to 0, that gave me an answer. But over here, I have only a 3 in front, and making that same equation gives me no solution. So basically, you can ignore numbers. You do not have to write down that you have looked at 3 and found it to never equal 0. You'll find after a while that you just will naturally ignore that front number. But what you have to be careful of is after a while, people forget to check, hey, is that an X in front? Then you are in trouble if you don't recognize it. So for the second factor over here, I subtract 4 so that I can solve for x, and I get an answer. For x minus 1 squared, I first have to square root both sides. And usually when you square root, do you remember you're supposed to put a plus or minus in when you do a square rooting? But what is the square root of 0? And then what's the difference between positive 0 and negative 0? Basically, That's the one time when you're square rooting where the plus or minus just gets discarded. And that happens, we're going to be doing a bit of comparing these equations with the graphs of the polynomials. But this happens when you're trying to solve while you're at a vertex of a parabola. And I'll explain more another time. So I end up with x minus 1 equals 0. I add 1 to both sides, and I got 2 answers out of this. And I probably should formalize and say, now, there are different ways that people will expect you to write answers. I'm not going to be picky about how you write your answers because there's a mathematically formal way to write it. There are informal ways to write it. I don't feel that this is the time in math to push you to write using these very standard, stiff mathematician notation. Just think logically about what you're doing, get an answer out. All right, how are you feeling so far? All right, not bad. So I move over here. And remember, the first thing is make sure that I have one side equaling 0. Now, I have 3 terms. And I need to first see, is there something that will divide all 3 terms that I can factor out? I can factor out an x, in fact, an x squared. And when I'm trying to figure out what's left, actually, let me write this down a little bit farther. When I'm trying to figure out what I have left, I'm going across the board and dividing everything by x squared. So x to the 4th divided by x squared plus 2x cubed divided by x squared minus 15x squared divided by x squared. Then I factor further. What I was able to factor out, that's always a done thing. Now I have a lovely quadratic. And you know why it's lovely? Because it has just an understood 1 in front of that x squared. That makes, oh, whoa, oh, you're answering the question too quickly. Hold on. So as I go to factoring this, maybe you see how to factor quickly, maybe it takes you longer. I need to be careful with the time. And if you need more explanation, you can see me in the, the office hours after class. So x plus 5 times x minus 3, positive 5, negative 3, multiply to make negative 15, positive 5 and negative 3 add to make positive 2. So that is properly factored. That's a quicker way of factoring, but it also leaves out a lot of thought processes that the diamond box goes through. Now, once you have factored as much as you can, then you have the step of take 1, 2, 3. Take each of the 3 factors and set them individually equal to 0. But remember, this only works when they're equal to 0. If they're equal to any other number, you can't just set them equal to whatever number's over there. That's why there's a special word or phrase, zero product property. And by the way, if you can do this a little bit faster than what I'm showing, I'm fine with that. So if you have x squared equals 0, what is that? Some of you might see really quickly what the answer is. If you don't see it quickly, then I'm going to do, again, what I did a moment ago. I'm going to say I need to square root both sides, and technically I'm supposed to do plus or minus when I do square root. That's going to leave me with an x equaling plus or minus the square root of 0. And what is plus or minus the square root of 0? Just plain 0, that's it. You do not have to, in fact, I would expect you to not do the square rooting that I just showed, but I wanted to make sure that you saw that the algebra behind it, the moves that we make when it's not a 0 on the other side, we're still making those same moves. It's just sometimes we can see a little bit faster. All right. Then subtract 5 from both sides to get x equals -5. And add 3 to both sides to get x equals 3. And I have 3 answers. X equals 0, -5, and 3. Woohoo! Then number 4. I do not have 0 on one side. So do you see what needs to be done first? How are you going to, what is the exact algebra move? You're going to both sides. Right, you're going to subtract 36x from both sides. So then I will have 3x cubed plus 3x squared minus 36x is equal to 0. Once it's set equal to 0, then you're ready to begin factoring, but always look for those common factors first. So if I look at my 3 terms, is there anything that will divide all 3? X will divide all 3 and a 3 along with that. So that's right. I keep forgetting to put that little down farther. So 3 times x is going to factor out. And to figure out what's in the parentheses, what I'm actually doing is dividing every single term by 3x. And, well, anyway, so then I get x squared plus x minus 12 and equal to 0. So I've managed to factor aside a 3x, and then I need to take this quadratic and factor it into 2 linear factors. So I'll factor a little bit quickly here. 2 numbers that multiply to make -12 and add to make +1 would be +4 and -3. I don't expect you to see it that quickly. It could take you some time, and that's fine. But now that I've factored, I take, yeah, no problem. Once I get that factored, then I take each individual factor, set it equal to 0, and solve. So I've got 3x equals 0, x plus 4 equals 0, x minus 3 equals 0. And by the way, if you can look at this factored polynomial and just write the answers, that's fine. I'm going to scroll up a little bit so I've got some room. And then divide both sides by 3, and it's still 0. Subtract 4, add 3, and I have my 3 solutions to that polynomial. And what I can tell you for now is when you're solving polynomial equations, if you are needing to factor something that is higher degree than 2, you will find a common factor of x or x squared or x cubed that can factor out of everybody. you are not at a point where you can deal with larger than second degree, solving for third degree or higher, that doesn't nicely factor an x out. And in fact, it's going to take us a while to get to the point where you're ready to deal with those. So for now, just be aware that it's always going to have a common x factor or an x squared factor, or maybe even an x cubed factor that'll bring it down to the quadratic that you're more used to. Alrighty. And what's in this class? Oh, about being able to factor when it's third degree or higher. We will do a little bit of it at the end of this unit. I recognize that this will be your first time seeing it. And if you continue on to an intro to calculus or pre-calculus class, you'll see it again, and you will have grown a little bit more in math to be more comfortable with it. Oh, the PSAT gang, huh? Okay. Now, very important, some parent graphs. This is going to start our process of learning how to graph polynomial functions, is to first look at the graph x to the n. In this situation where n is even, and in a moment where n is odd. So the first thing you're going to do is fill in the chart. Yeah! Go table. So, what is -2 the number squared? And you know what? Let's save our time. Let's take -2 and +2 and say square both of them. When x is -1 or +1, and I square those numbers, I will get the number 1 for either one of them. And 0 squared gives me 0. Now you're familiar with the function x squared. And I'm going to plot those points. And lightly draw a lovely little parabola. Hi, look at me. I'm a cute little parabola. Yay! Then we're going to take a look at what we get with the table when we have x to the 4th or x to the 6th. And I'm going to do this in pairs. -2 and +2. What are both of those numbers to the power of 4? Good, 16. Then -1 and +1, what are those to the power of 4? +1. And then 0 to the 4th power. Well, I'm not going to be able to plot all these points, am I? I'm going to plot, hey, look, they share points. But when I'm at -2, this graph is way up at 16. So based on the fact that it's way up at 16, I know that this is far steeper. But then, what about down here, if I am comparing them? It's actually going to make it boxier and steeper. If you're between -1 and 1, putting something to the second power versus the fourth power versus the sixth power is causing the denominator to get really, really big. And if the denominator is getting really big underneath a 1, then you are dealing with smaller y values for my x to the fourth graph than my x squared had. When we go and do x to the sixth power, it's going to be even more extreme. It's going to be boxier than we had for x to the fourth. And it's going to be steeper when it gets out here. Now, I'm doing like a halfway decent job graphing, but I'm saying halfway, more like a quarter. I'm going to show you what these graphs look like. And hopefully you filled out this table as well, but I'm going to go over to the answers because, again, I'm concerned with time. And here's what they genuinely look like. And anything that you don't get written down in notes, that it is posted on the classwork. If I'm going to hit 64 for x equaling +2 and -2, how steep is that going to make x to the 6th go? And I just want you to see how they get boxier the higher the degree. But what actually matters here is for you to see what they have in common, not so much as how they're different, but what they have in common. They have in common that they basically are above the x-axis, touch it at one point, and then bounce right off of it. That is the most important thing for you to see about these graphs as we prepare for graphing polynomial functions. Also notice that all of them go through the same 3 points. Doot, doot, doot. The domain is all real numbers, but the range, if I'm dealing with x to the power of an even number, the range is going to be only 0 and higher. I have a vertex at the origin, and I wrote down a couple of other shared points, or the 2 shared points, just to emphasize that all graphs that are x to the n, where n is 2, 4, 6, 8, 10, and so on, they all share 3 points. The vertex, and then those 2. Okay, when n is odd. Okay, it's 137. When n is odd, we have graphed x cubed already. So I'm going to write that out kind of quickly. I've got when x is -2, I get 8. When x is 2, I get, you know what, I should write and not speak right now. There we go. I get those when I plug those x's in, and we've seen this before. I'm going to plot those points. And then I'm going to draw that x cubed graph that kind of goes and steep, la 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 la, and steep. I can. And this is why I grant a bit of forgiveness on your own graphs when I grade them. It's just realize that you do have the time to make it look better if you realize that it looks far from what it should. Okay. Then x to the 5th, do you think it is going to look similar? Where are we? we are at x to the n where n is odd. And so I'm looking at graphing x cubed, x to the 5th, x to the 7th. And I can look at what these numbers are, and I'm going to have to show you the answers a little bit faster than I would like to. And so, yeah, I just need to go over there. When I have x to the 5th with 2 and negative 2, it's very big, but x to the 7th is crazy. So what you want to see is that once I get past, I've got these 3 center points that all of these x to the odd powers go through. Once I get past them horizontally this way, the higher the exponent, the steeper the graph. But if I'm dealing with numbers in between 0 and 1, the higher the exponent, the more flat it is. Because if you're taking a number whose absolute value is smaller than 1 and you're multiplying it a lot of times, you're making a very, very, very small number. Now, what is the most important thing that I want you to take from this? When you have x to an odd exponent, it starts, if I go left to right, it comes up out of negative infinity and then gets to the x-axis, it kind of wiggles. It goes, wee! And then it keeps on going. What dance move would that be called where you go, and I know I did not do that well. Shaking your head at me. The worm, thank you. So x cubed does the graph like the worm. It goes, wee, worm, as it's going through the x-axis. This is going to be very important when we get to the point of graphing polynomials in general. These two things that we see happening right here. The even power versus the odd power is whether I bounce off or do the worm dance through the x-axis. And then do be aware of the domain range. And it has the inflection point like x cubed had, and they always share the points 1, 1, and negative 1, negative 1. We're almost there, people. I see some of I'm really, really tired of this faces. I know. Okay. Yeah, but we'll get there. Okay, I have like 3 minutes left with you, so I need to kind of get on with it. So I'm going to kind of take you through the answers. I'm going to have you graph x to the n powers, and I do not expect you to draw perfect graphs. You're just getting a feel for them. Computers are going to graph them well. When you draw them, you're showing that you understand their nature, so that because you want to learn what to expect out of certain functions. What should they be looking like? And the computer can draw them for you, but you need to be aware. So draw just a boxy, squishy x to the 5th that goes through these 3 points. Do you remember what you do to a graph if x is divided by 2? What is that going to change on the parent graph? If x is divided by 2, then what am I going to do to my x coordinates? And Right. You're going to multiply them by 2. When it comes to things that affect a graph horizontally, it's always the opposite operation. And I feel like I've lost some of you, but yeah, I've got 1 minute left. So the points that were at x equals 1 and x equals -1, they're keeping their y value, but they are doubling. Whoops, I put that other one in the wrong spot. They are doubling. However, when x is 0, multiply it by 2 all you want, it's still going to be 0. And then you're going to take that function and move it left 1, down 3. I recommend that you take these 3 points, redraw them over here, and let's see if I can, and then move each of them left 1, down 3, and you'll have it. Now, the answers are online, and I know I'm out of time. Luckily, though, I got through the parent graphs with you, and you've done transformations before. So the answers, again, are online, and you get extra time to get your homework answers done because I didn't put them up. I failed to upload them. This class is over at 1:45, correct? Today is Thursday, so yes. So I can't hold you any further. Finish that up and get that turned in tonight or by tonight. And I'll see you later.
Bye. Thank you.
Bye.
Bye. Thank you.
Did anyone have any questions before I go? You're muted. I don't know what you're saying. Oh, screen cap.